today we're going to do a tutorial for how to analyze the data that comes out of a competition ELISA, like our paralytic shellfish poisoning ELISA or Saxitoxin ELISA. When you download your data, so this is after you've read your plate at 450 nanometers, when you download your data, it'll look something like this. Different plate readers spit out the data differently, but this is how ours looks. And the first thing I do is set it up so that I know what I'm dealing with here. So I delete out all this extra information I don't need, all these zeros. These are just empty wells I didn't read. The first set of data here is my standard curve, and so I'm going to label that. It's in Saxitoxin in nanograms per mil. And it starts at 2, that's our highest concentration, and each one is, each subsequent dilution is half of the other. So we can use Excel to calculate what our standard curve is, with 0 being the lowest or the highest OD. Then we have a series of unknown samples here, and I'm just going to drag them down there. All right, now the easiest way to do this is if you have a program like GraphPad. GraphPad Prism is fabulous. It calculates your values for you, runs your standard curve. So let's start with that. You have GraphPad, you open the program, you'll have to select Y. We have all of our data in duplicate, so we have 2 replicates side by side. Create a spreadsheet. Then we're going to grab our standard curve and put it in here. Label this Saxitoxin concentration. And then we're going to take our unknowns and set them in the spreadsheet too. Now there's no concentration value here, but that's okay because we're going to use the standard curve to calculate what the concentration of our unknowns are. All right, so you click Analyze. We'll do a nonlinear regression curve fit. We're going to choose the sigmoidal equation where X is concentration. And then the important thing here is to click Interpolate Unknowns from Standard Curve. And that's what's going to allow GraphPad to calculate the nanogram per mil Saxitoxin equivalents of our unknown samples. So click OK. The first thing I always do is I check my graph. And to make sure my graph has a nice curve here, that looks fabulous. Click OK. And then when I go to my results, I can look at the interpolated X mean values here. And here's the average optical density that we measured in our plate. And here's our concentration. So I'm just going to grab that, put it here, highlight it in yellow so we can see what we're looking at. And this is our concentration. Nanograms per mil. Great, fabulous, ready to roll. Now, the problem is if you don't have GraphPad, and if you don't have GraphPad, then what you have to do is calculate it in Excel. So I'm going to show you how to do this. Let's start a new spreadsheet here. A new set here. All right, in order to be able to do this, we have to calculate the average of our replicates. So I'm going to make a little space here, do average optical density for each value that we can then graph. And we will plot this using Excel. So go to Insert, add a scatter plot. And again, if you look at this, you go back to GraphPad, look at our graphs, see they look exactly the same. So we're on the right track here. This is our average OD. Let's try that again. All right. So to calculate in Excel, you add a trend line. And we're going to add a linear one, but I'm going to ask it to to display the equation on the chart and display the R² value for us. And I'm going to make that a lot bigger so we can see what we're doing. All right, now as you can see here, the R² value really isn't very good, and that's because it's not really a linear curve, at least not in this format. If you use this equation to calculate your values, let's go ahead and do that. Let's calculate our average OD. For our samples. And remember, OD is going to be your Y value. So to calculate X, which is concentration, you just use your linear equation here, where we have this value minus our y-intercept, 0.52, divided by negative 0.2321. And that calculates what our concentration, actually let's put this over here, it's here, concentration in nanogram per mil. And if you're looking at our GraphPad, where we had a very nice line that fit our curve, you can see that these values are really different. There's a lot of variability between these two. And the reason for that is that this linear equation is not a good fit for this data. So the better option is to log transform it. And I'm going to do that manually again, just because it makes it a little easier to calculate the values. So let's go over here, make some more space. And this is going to be the log concentration for my standard curve. And of course, you can't log 0. I'll show you in here in a minute what happens if you try to do that. But we'll use the log 10 formula in Excel. Drag that down for us. And what happens is if you try to log your 0, it won't work because you can't take a log of 0. So it's really unhappy. In order to do this, you can create a lower number like 0.01, or you can just leave the 0 out. As you can see, it doesn't really matter because your unknown values are not between 0 and 0.03 nanograms per mil. So remember, this is Saxitoxin in nanograms per mil. All right, so let's graph our data. This time we want to make sure we're graphing the average OD. Insert a scatter plot. And this time you can see, I'll get it to move over a little bit here and compare these two graphs. It looks a lot more linear. And again, you can see why you don't really need the zeros, because down there it's not, the curve is leveling out. So this is average OD, but it's log transformed. And this is the way that you would calculate your data, especially here for this nice linear region. Let's add a trend line. And again, we're going to click more options so that we can do linear up here, but we also want the equation on the chart and the R² value. And when you do that, let's make it really big so we can see what we're dealing with. You can see that the R² value is much closer, it's 0.96. If you really wanted to make it even better, you could get rid of some of these lower values, 0.97, 0.98, and that's okay as long as your optical densities are all within this linear range. But let's just not do that for right now, just so you can see how this works with this formula. So if we're going to do that, And we'll use the same formula we did before, where our Y value is this optical, the average optical density for our sample. We're going to subtract the y-intercept, which is the b in the y equals mx plus b, divided by slope, -2599. Now that looks really different, doesn't it? But that's because it's in log. Remember, always remember you had a log transformation. So this is actually your log concentration here, not your actual concentration. And then what you have to do is take that value you get and you do 10 to the little hat that power. Now you get concentration. And this is the values that you want. And you can see, if you compare it back over to GraphPad's values, this one is far closer than our linear equation that was not log transformed. And I suspect you can get it even closer if you remove some of those higher points here. So you have to be very careful if you're going to do that, if you remove the lower concentrations, because you just need to make sure that your samples all fall within the linear range of your standard curve. So let's try that and see what happens if we take the lower ones out. Let's just remove these two. So we have a nice linear range. I'm going to be very careful here. My highest OD for my lowest concentration is 0.5. None of my samples are higher than 0.5, so I'm safe to use this. Now let's use that equation. So again, equals, this is optical density is our y, minus point, this time it's 2113, divided by -0.3225. And remember, that's log transformed, so we do 10 to the power. And now, because I'm running out of space here, I'm not sure, let's make it a little bit bigger, see if I can get it all on one screen. There we go. That's real close. So that you can see the values get a little closer to what our GraphPad was able to calculate. So they're a little more accurate when they're within the linear range of that standard curve. But you just have to be careful when you start taking away points, that you don't take away points that your data falls within, or you won't be accurate. If that happens, then you either need to stop your curve sooner with the acid stop so that it becomes linear at those lower concentrations, or use a program like GraphPad that can do a sigmoidal calculation response, a sigmoidal curve calculation rather than linear. All right, so reach out to us, let us know if you have any questions, and I hope you enjoyed the video.